Groundwater. Groundwater is water beneath the Earth's surface, within saturated soil and rock, and it supplies wells and springs. It's refreshed through infiltration, which is the slow downward movement of water into the groundwater. And notice in this picture, it's not an underground river. It's not empty space down here that's just water. This is soil, and it's wet soil. Some things to notice about the groundwater. Here we've got a cross-section of the groundwater in a landscape. Wherever the groundwater meets the surface, you get standing water. This surface of the water is called the water table. It's higher under hills. It flows downward, and it pops up above the ground, and that's why we have water above the ground in streams, springs, and ponds. Here's a close-up of the groundwater. These yellow points are meant to be soil particles. The top here, we have the zone of aeration. Notice around the soil particles, it's blank, meaning there's air there. There's no water in this section of the soil. Beneath that, here's the blue, the zone of saturation, where the pore spaces in the rock are filled with water. And the border between them is the water table. It's the boundary between the zone of saturation and the zone of aeration. If you're going to drill a well into this, you have to go below the water table. And in fact, the deeper you go below the water table, the better. Because if you get more rain, the water table goes up. If you get less rain, the water table goes down. Beneath these is the confining layer. This is the solid bedrock that prevents the water from sinking any lower. Alright, talking about wells. Here we have a well drilled into the ground, and there's a water table. When we sink the well in, we then start pumping water out. This is the surface of the water table. And notice that right around the wells, it's depressed. The water table drops down. That's the cone of depression. Cone because it's a cone shape, and depression meaning it's low, it's down. It happens because it takes a while for the water to flow through the soil. And it's just like when you are drinking a Slurpee, and when you drink too fast and all of a sudden the area right around the straw becomes empty of all the good flavor. That's the same idea here, so please draw in the cone of depression. The flavor has been sucked out right next to the well, and that's the cone of depression. Now, one of the important terms when we deal with groundwater is porosity. It's the amount of open space. And there's only three things that affect porosity. Shape. Round particles don't fit together as well as angular ones, so round particles give you a greater porosity. Packing. The more closely packed the particles, the lower the porosity. And sorting. Unsorted materials have less porosity, as the small pieces fill in the gaps between the bigger pieces. So let's practice this a bit. This soil, if you notice, is unsorted. There's big, medium, and little pieces. So the air in between isn't nearly as much as if there had only been these larger gray particles. All of this space has been filled in with the other different types, so you end up with a lower porosity. In this set, A and B, they're both round shape. They are sorted, both of them, but A is less tightly packed, so it has a greater porosity. Here, They're both sorted. They're both the same. This is all the same size. This is all the same size. This is round. This is round. Their packing is the same, rows and columns. So they have the same porosity because the sorting, shape, and packing are the same. If the shape, sorting, and packing are the same, does porosity change? No. Size doesn't matter to porosity. The amount of open spacing here will be the same. It's 48%, 48%, 48% when you've got round that are packed in this rows and columns. Permeability is how quickly water can travel through a material. Larger pores have higher permeability. Size does matter for permeability, not porosity, but it does matter for permeability. So let's take a look. Here we have 1 meter each of gravel, sand, silt, and clay. We're going to drop some water on it. The gravel, larger particles, the water gets through it in about 2 minutes. It starts coming out. Sand, smaller, 200 hours. Silt, 200 days. Clay takes 200 years. So we say this has a high permeability, and the clay has a very low permeability. In fact, we might call it impermeable, not permeable. Again, porosity is the amount of empty space. These have low porosity. They're solid glass or a solid block with one hole, low porosity. High porosity would be styrofoam, lots of bubbles, or this mesh. Permeability is different though. These, whether it's a low permeability or high, if those bubbles don't attach, then the water is not going to flow through it. So both of these are low permeability. Here, even though there's only one hole, it's a nice hole, water can flow through it. So, and the water can flow through mesh as well. So now we're going to talk about some wells. There's different types of wells because we have different types of aquifers. This is what we call an unconfined aquifer. The aquifer is exposed, it's directly infiltrated all along its length, whereas this down here is a confined aquifer. There is a confining layer above it and below it, and so it actually is under pressure. Whenever you have a well that goes into a confined aquifer, we call that an artesian well. And if the well is below the surface of the water table, then it flows. This is a flowing artesian well. Again, artesian well is a well that drills into a confined aquifer because it's under pressure. It flows if it's beneath the water table. So here's some examples. This is a confining layer. This is a water table well because it doesn't have a confining layer below it. This one is an artesian well because it drills down into the confined part. This is under the confined part. But notice this is the water table. Since the water table is below the surface, this well doesn't flow. You have to pump it. But this well is a bit of a gusher. Caves. Caves are pretty cool. All about them in Virginia. Happens from extensive chemical weathering of limestone, the calcite. Calcite dissolves, as we've discussed in class, and you get a cave. We get various formations. The most important probably are stalactites that hold tight to the top, and stalagmites that grow up from the bottom. Luray Caverns is a good example, as is Skyline Caverns. And since we've got all those caves in Shenandoah Valley, it's what we call a karst topography. It's an area with lots of sinkholes and fissures and caves. The caves collapse at the surface, which gives you sinkholes. You can have sinking streams, disappearing streams, sinkholes. It's really interesting looking underneath the ground. Not necessarily the safest place to live, though. What happens first is the groundwater dissolves, dissolves the limestone, producing caves. And then the ground above the caves is eroded away, and eventually the ceiling of the cave collapses, and you get a sinkhole. That can happen because of erosion. It can happen if you pull out all the groundwater. This house is pumping out all the water, which dries this area out. And you know a dry cracker is going to break, or a dry cookie is going to break a whole lot easier than a wet cookie. Same idea. Or if you just build too much on top, then it'll collapse. Karst topography, again, another image, disappearing stream going into these caves. More caves. This is a sinkhole. This is one in Winter Park, Florida. Florida is also known for many sinkholes. It's a nice, good size. This is a 4-lane highway here. Tree that fell in. This is part of a warehouse that fell in. This is a sinkhole in Shenandoah. Again, you want to be careful where you're building in a karst topography. There are other dangers with groundwater besides the ground just falling out underneath you. One of them is the effects of overpumping a well. Here we've got that original water table. Someone moves in and starts pumping, and you get a cone of depression. Fine. But eventually, you have to pump more and more and more. Notice his well barely gets to the water table. If you get a dry year, he's going to dry out, so he has to dig a deeper well, and the level of the local stream is going to drop. Here we have another one, farmer pumping water, and Bill Gates moves in across the stream, and he pumps out a bunch more water for, who knows, a bunch of pools and fountains and stuff, and the water table drops, the stream gets lower. Yes, I know the tree is getting bigger. That's because years are going by. Then a factory moves in instead, and that really drops the water table. So overpumping removes too much water, allowing the water table to dry up. The water table drops, the water streams dry up, and it can create sinkholes and dry out the soil. Examples from the Great Depression. These are smaller sinkholes from too much groundwater being pumped out, and this is a dust storm, the Dust Bowl in Kansas. Another option, here we've got that water table, and somebody builds a mine, a quarry, an open pit, and they dig deeper because they're taking rocks out, and now they have to pump the water out so that their machines don't rot. Well, eventually that gets kind of expensive. So it gets too expensive to pump the water out, so they just stop, they close up the mine, and you're left with a great big pit, and everyone throws their stuff into open holes. It's just the way it is. Unfortunately, cars, refrigerators, you will see just about anything dropped into any hole in the ground. Car has lots of nasty chemicals in it. Oil, gas are just a couple. There's also antifreeze and battery acid and all sorts of stuff. And that now gets into the groundwater. And where's it headed? To our well. And it flows further downstream. This is an exact example of what happened at Hidden Lane landfill right here in Sterling. Also, when you have acid rain produced from factories, cone of depression actually draws all of your pollution towards the well. Alright, here at the ocean, like down at Ocean Beach, Virginia Beach, or Ocean City, here's the water table, and it meets the ocean. This is salt water. Blech, not something you want to drink. This is fresh water. What's nice is the salt water is more dense, so it goes underneath. So you build a well right here. It doesn't go down to the salt, it's right up here. And you start pumping, pumping, pumping. Trouble is, if you pump too much, then the salt will be pulled up towards your well, because you're sucking it out, your cone of depression is getting lower, and you can actually reverse this flow and pull salt into your well. That saltwater penetration is really, really bad for both your pipes and your drinking. So to wrap it up, here we have a hill, topographic map. Here's the hill, and there's Briar Bay down at the bottom. T is a toxic waste type. You can hear a side view, above view. A, B, C, and D are water wells around this toxic site. Here you can see at least A and C along the line. In what direction will the pollution flow? Downhill, which in this case, if you assume south is the bottom of the map, southeast. The well that will be contaminated first is C, because that's the closest one downhill. There's many ways it can be cleaned up, but they're all hard. You can just dig up all the soil. Let's dig up a hill and wash it and clean it and then replace it with good soil. Not exactly easy. You can squirt more water in and suck out the polluted, more water, suck out the polluted, and end up essentially cleaning the soil in place again. Pretty hard to do. You could also build barricades underground, trying to stop the water from the polluted water from making it to the bay. But none of them are really great options. So once you hurt the groundwater, you really run the risk of not being able to clean it up again. And so that's it.